So now that we understand the basics of Raman spectroscopy, we can go ahead and interpret the Raman spectrum of methane. And so, the starting point for this is very similar to what we did when we were looking at the IR spectrum of methane. We actually haven't done that in complete detail yet, but at least we talked about the different possibilities and the different normal modes. So you need to know the normal modes first. And so, we're at the same starting point. There was some problem solving to get to this point, but for methane, the normal modes are A1 plus E plus 2T2. Which of those normal modes are Raman active? And so, just like for infrared spectroscopy, in Raman spectroscopy, we have an intensity integral, but the transition moment operator here is going to be a product of two Cartesian coordinates. And so remember, for IR spectroscopy, the transition moment operator was the X vector, the Y vector, or Z vector, specifically for X, Y, and Z polarized light. For Raman spectroscopy, it's going to be any product of two Cartesian coordinates. So this could be X squared, Y squared, Z squared, XY, YZ, or XZ. Those are all the different possibilities, okay? Now, the really nice thing about Raman spectroscopy as compared to IR spectroscopy is that overtones and combinations are generally very weak. And so we actually don't have to worry about those most of the time at all, at least when you're talking about liquids or solids. In gas phase, they tend to be, they can be a little bit stronger. But because these are scattering techniques, right, it's a little bit harder to kind of scatter in combination. And so for that reason, the Raman spectra are a lot easier to interpret in most cases than the corresponding infrared spectra. So again, we have this intensity rule, right, just generally for vibrational spectroscopy, where it's an integral of psi initial times the transition moment operator times psi final times d tau, the differential across all space. Psi initial, remember, is the ground state wave function that's always totally symmetric. So it gets a symmetry of A1 or A1G, something like that, ones across the board. And so because we're timesing everything by 1 in psi initial just drops out of the equation. And we're talking about this excited vibrational state, which nu equals 1. And so our selection rule, again, is only going to be if these two things, mu and psi final, have the same symmetry, right? Because only then are you going to be on the diagonal in the product table. Only when you're timesing something by itself in terms of its symmetry will you get an A1 in the product. And only when you have an A1 in the product will you get a non-zero integral and thus have a chance of seeing a peak. And so the selection rule then, I is only non-zero if mu times psi final contains a totally symmetric representation, which only happens when psi final and mu are of the same symmetry. So we've gone over this slide before. I just put it in here again because we're about to go over selection rules for vibrational spectroscopy, or for Raman spectroscopy. And so when we ask the question, which of the following Raman modes are active for methane, and we know our normal modes to choose from are A1, E, and two different T2s. We just have to look for those that have squares. And so this one has squares in it. It could be squares or any product, so XZ, YZ, okay? So A1. A1's our first normal mode. Is it Raman active? Yes. We have products, A1 transforms as a quadratic equation. Is a quadratic function is the best way to put it, okay? We don't have any A2s, but if we were to have an A2, it wouldn't be Raman active or IR active. E is our next one, and E, again, is Raman active. We have quadratics in there. We don't have any T1s. Would T1 be Raman active? No. There's no quadratics in here, just rotation functions. And then we have two T2s. Are they Raman active? Yes, we have quadratics in there. So all of these normal modes, A1 plus E plus the two T2s, are going to be Raman active. Okay? All four modes are Raman active.